This video details adaptive cruise control or ACC systems and explores the integration of automation within cars. We are from Group 10. My name is Chou Chou and my group members are Yap Han Ze, Felicia Lau Yee Siew and Wei Hung. In this video, we will discuss the principles of adaptive cruise control systems and propose our own design. We will present and explain the flowchart and block diagram of our system, as well as the functionality and working principle. Potential discrepancies faced by adaptive cruise control systems are also addressed with suitable solutions. What is an ACC system? An ACC system is a form of Advanced Driver Assist Systems or ADAS that helps the driver maintain vehicle speed and a safe distance with the vehicle in front. About the history of ACC systems, in the 1990s, Mercedes invented the first radar cruise control system capable of modulating the speed of the vehicle. It was implemented in the S and CL models. In the mid-2000s saw a surge by various car brands towards research and development of ACCs. Stop-and-go functions were introduced, and in the 2010s, ACCs became widespread in consumer vehicles, with economy cars offering ACC systems as standard. The system is easily accessed where it is activated by buttons located on the steering wheel. The driver can select the preset speed the car maintains and the safe distance with the car in front. The basic structure of an ACC system uses a combination of sensors, which are radar and speed sensors, that transmit data to the controller or ECU, where it activates the actuator, which are the braking system and vehicle drivetrain. The radar detector emits radar waves that hit the car in front. The time taken for the radar waves to travel back to the radar detector is processed as the distance. In short, the radar detector measures the distance of the vehicle with the vehicle in front, where the data is then sent to the ECU. The ECU compares the measured distance and the safe distance chosen by the driver. The brakes are applied if the vehicle is too close to the vehicle in front. This is achieved through the connection between the ECU, the brake actuator module, which is connected to the braking calipers of the vehicle. The system will accelerate the car back to the selected speed when the car in front accelerates as well.
The radar sensor is typically installed at the corners of the front and the rear of the vehicle. It permanently monitors the road ahead and helps maintain a safe distance from the vehicle in front by adjusting the car's speed. By installing the radar sensors at the corners of the vehicle, it helps to detect position, relative speed, and direction of movement of other traffic participants and objects from a distance. During assisted and automated driving, the vehicle must know what is happening at its surrounding at all times. It must be able to detect objects and people and react appropriately. The camera utilizes an innovative and high-performance system. The multi-paths are, for example, following technical path for image processing in parallel. The first path is the classifier for pattern recognition. Here is the typical appearance of objects, such as vehicles, cyclists, road signs, or lane markings are already learned in advance. If an object of this kind is detected, it will be classified and marked. For the second path, the camera utilizes the dense optical flow and the structure for motion to detect raised static objects, such as parked vehicles. The third path relies on artificial intelligence-based method. Through AI and machine learning processes, the camera classifies objects and differentiates between surfaces on the roadway and the edge of the road. The control module, also known as the ECU, Electronic Control Unit for ACC, is the central processing unit of the system. Based on the processed data, the control module calculates the distance to the vehicle ahead and determines the relative speed difference. The control module decides whether to accelerate, decelerate, or maintain the current speed. After making a decision, the control module sends commands to the throttle actuator to adjust the engine power for acceleration or to the brake actuator for deceleration. When the control module determines that acceleration is needed, it sends electronic signals to the throttle actuator. The actuator then adjusts the throttle position to control the amount of air entering the engine, thus regulating the engine's power output and vehicle speed. On the other hand, when the control module determines that deceleration is needed, it sends electronic signals to the brake actuator. The actuator then applies the brakes as required to reduce speed and maintain a safe following distance. On the other hand, Vehicle speed sensor, also known as the VSS, is used to measure the rotational speed of the gear in the transmission system. The VSS provides the necessary information for the ACC control module to regulate the vehicle speed accurately. This ensures that the vehicle maintains at the set speed or adjusts as needed based on the traffic conditions. The steering wheel controls help the users to interact with the adaptive cruise control system without taking their hands off the wheel. The button and users are shown in the picture on the right.
This flowchart illustrates the sequence of steps involved in the adaptive cruise control system, providing a visual representation of the process flow. It begins with the initialization of the ACC system, followed by scanning the surroundings for vehicle using sensors. Upon detecting a vehicle, the system calculates the distance between our vehicle and the detected vehicle, and if the distance is not within safe perimeter, the PID brake is activated to slow down our vehicle and increase the distance to a safe level. Once the distance is between the safe parameters, the system then calculates the speed of both our vehicle and detected vehicle. If our vehicle speed is higher than the detected vehicles, the PID brake is applied to match the target vehicle speed. Conversely, if our vehicle speed is lower than the detected vehicles, the PID throttle is activated to increase our speed to match the target vehicle. The system will continuously monitor whether the driver takes control of the vehicle, and if the driver does not interfere, the process of maintaining a safe distance and matching speed is repeated. If the driver takes control, the ACC system deactivated and the vehicle switched to manual driving mode until the ACC is reactivated. Moving forward, we have the block diagram of the adaptive cruise control system, which illustrated the primary components and the interaction within the system. We begin with the driver input, where the driver activates the ACC system, the radar sensor that detects the surrounding vehicle. The detected vehicle data is transmitted to the data processing unit or the electronic control unit. Here, the information is analyzed to determine the relative speed and distance of the detected vehicle. The data undergoes vector control, which transforms the three-phase stacker current into a two-coordinate DEQ rotating reference frame. This transformation allows for independent control of magnetic flux and torque-producing current component. Next, we have the inverter, which is an electronic device that converts direct current to alternating current. In electric vehicles, the inverter adjusts the frequency and amplitude of the AC power, generating the necessary pulse width modulation signal to drive the motor based on the control input. A feedback loop with a current sensor measures the current flowing through a conductor, providing a real-time feedback data to the control system. The external factors, which is known as a disturbance, can affect the system performance of the vehicle. In the context of adaptive cruise control, a key disturbance is the velocity of the leading vehicle. This stimulates the real driving conditions where the leading vehicle may suddenly change in speed, impacting our vehicle speed control. The adaptive cruise control system uses this disturbance data to adjust its response accordingly. The process signal is then sent to the actuator, which include the PID throttles and PID brakes. Depending on the situation, either the throttle or brake is activated. For instance, if our vehicle speed exceeds that of the detected vehicles, the PID brakes is activated to decelerate until both vehicles match the speed. Conversely, if our vehicle speed is lower, the PID throttle is activated to accelerate while maintaining a safe designated distance. The actuators transmit the mechanical power to the wheels, causing the vehicle to move at a desired speed. A vehicle speed sensor continuously measures the vehicle speed and provides a real-time data back to the electronic control unit. This speed data is compared with the desired speed set by the adaptive cruise control system, ensuring that our vehicles maintain the desired speed and adapts to change for efficient operation. This process repeats throughout the journey until the system detects that the driver has taken control of the vehicle. At that point, the vehicle switches to manual driving mode and the adaptive cruise control is deactivated.
Moving on to some of the problems of the adaptive cruise control system, it can be said that the ACC system is very susceptible to interference from other vehicles. This is said because the ACC system cannot correctly predict the human nature of a driver. The ACC system can be disrupted by the behavior of other vehicles such as the aggressive driving, frequent change of lanes, and vehicles with well-functioning sensors and emitting incorrect signal, which lead to incorrect decisions made by the system. To solve this, enhancing the robustness of the ACC algorithm to handle such interference and integrating V2V communication into the ACC system to improve the reliability of the system. V2V stands for vehicle to vehicle. V2V allows the vehicle to share information directly with each other, providing data such as speed, position, directions, etc. This can help the ACC system to receive early warnings and process the information in a prompt to avoid potential hazard. But it is not only limited to V2V. There is also V2I, vehicle to infrastructure, and V2X, vehicle to everything. With V2I, it can allow the vehicle to communicate with the traffic light and such, to obtain information like the remaining time for the traffic light to turn green or red. An example for V2X is vehicle to pedestrian. By knowing the distance between the vehicle and the pedestrian, it is possible to know when a pedestrian is crossing the road suddenly and allow early warning for the vehicle to come to a stop. With this information available, it can increase the safety for all road users. Another problem faced by ACC is the integration with other advanced driver assistance systems. This is said because the ACC system needs to work seamlessly with other ADAS systems such as lane keeping assist and automatic emergency braking. This is said because the ACC needs to handle the emergency braking if the vehicle in front were to collide with another car coming to an instantaneous stop. Therefore, the ACC needs to make sure that it is able to do this to ensure the safety of the driver and the passenger. To solve this issue, by integrating an ADAS platform where all systems like previously mentioned adaptive cruise control, automatic emergency braking, can be controlled cohesively and data can be shared among each other to enhance the overall safety and performance. Another solution to this is to integrate human-machine interface. By integrating a unified and intuitive HMI that provides feedback and alert to the driver about the ADAS features, this can also keep the driver engaged about the status of the ACC, such as the distance and when a car is experiencing braking. This can prevent the driver from being too reliant on the ACC and ADAS feature, causing the driver to lose focus when driving. Reminders to keep the driver's hand on the steering wheel or face direction detection can be implemented to ensure that the driver is constantly focused and not fully reliant on these features. By incorporating the human-machine interface and V2V, V2I, and V2X data into the system, we are able to solve the issue of interference from other vehicles and drivers over-reliant on the ADAS system.
That's all for the video. Thank you for listening.